Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
In our previous video tutorial, we included a Sentinel 2A daytime image of our region of interest, and we identified visually via the daytime imagery locations of snow via that Sentinel images. And then we overlaid that, or we compared it with the Terra snow cover product and all the terrain and climatic characteristics, and it formed a nice coherent holistic picture of locations within our region of interest that will have snow and will most probably have snow going forward if those parameters, terrain parameters and climate parameters are met. Most probably then it will snow there. Okay, so we've looked at the daytime imagery. We then looked at different periods. For example, we looked at the 21 period, we looked at the 22, 2023 period, etc., etc. And we visually, by looking at the daytime images, we can look at locations, and then we then overlaid it with all these other images that we created. So that was quite neat. But there's also something that's called the Normalized Difference Snow Index, NSDI, the Normalized Difference Snow Index, NSDI. Okay, there's something like that, and basically it uses spectral reflectance to generate locations that most probably will have snow or does have snow. Similar to the build-up index, normalized difference, difference vegetation index, etc., etc. So, and I think we did it in one of our daytime images. We looked at generating a lot of these images, but that was specifically related to build-up areas. Now we get a normalized difference water index, a normalized difference snow index, etc., etc. So that's all up. And the idea is you manipulate the spectral reflectance of the different bands to get a index. Okay, so that was quite neat. So we can do the same now in this episode, in this video tutorial. So if we go to the normalized difference snow index, this one here, it says that, and remember you calculate for Sentinel, not for Landsat, because you're working with Sentinel images, and as I said in the previous video tutorial, the reason is because of the high spatial resolution. Okay, so what is the formula for it? It's band 3 minus band 11 divided by band 3 plus band 11. Now what is band 3? Band 3 is the VIR, and band 11 is the shortwave infrared. So this is the visual infrared band, and this is a shortwave infrared band. And what it basically says, values above 0.8 of 0.42 are normally snow. Okay, so what we're interested in is to use the Sentinel image that we've created for our region of interest for that particular period. We generate that equation, we calculate the NDSI, and then we compare it to see what the number looks like. And if it's, as I said, generally, as this particular article suggests, if the value is above 0.42, then then there's likely of snow, etc., etc. Okay, so let's see if we can calculate it. So we're going to generate a normalized difference snow index ourselves. Okay, let's have a look and see if there's anything interested in this specific. Nope, nothing serious about this. Okay, so what we're going to do in this particular video tutorial, we're going to calculate our own normalized difference snow index with our image, our Sentinel image, but we're also going to use the already existing data product, the normalized difference snow index data product that's already existing in our Earth engine. We're going to use that as well. So we have our Sentinel image for our given period, for our locations, which we visually can identify snow, and then we're going to bring into our equation or our images, we're going to bring in the normalized difference snow index, that data product that exists in Earth Engine, but we're also going to calculate it ourselves using the Sentinel image that we've already that's already in our project. So we're going to, and then we're going to obviously compare the two. Now, interestingly here, the data product, the normalized difference snow index data product is only available till February 2023. Now that's a bit of a problem, and this is where it becomes a little bit tricky now, because most of the snow, or the heavy snow in recent times, was in 2023, 6 months, 7 months, 8 months. So this won't include that. So unfortunately, our biggest snow month, that's a period in 2023, that's now excluded from our calculation. Then there was a very, very big snow period in 2014 and 2016. But unfortunately, the Sentinel images is only available from 2017 onwards. So unfortunately, we have a period of 27 till 2022 that we can look at. And in that period, 2017 to 2022, there's only a little bit of snow that happened in 2021. So this, let's call it, complicates our thing a little bit, because the big snow periods lies outside, and I want to have a period where I can generate all the images, not just a particular image or a couple of images and leave other images, because it's all about creating the holistic picture, and everything must gel, so to speak. Everything must come together. We've already seen that the climate ones only goes to 2022. So 2023 is out. We can have two images or two variables not available for 2023. So that's not good. We can go to 2016, and all of them are available except Sentinel. And if Sentinel is not available, then our derived snow index from Sentinel is also not available. So that also is two unavailable. So that gives us a window from 2017 to 2022. Now, unfortunately, in that window, 17 there was no snow, 18 there was no snow, 19 there was no snow, 20 there was no snow, 2022 there was no snow. There was only a little bit of snow in 2021. So fortunately, if none of these periods had snow, we would be snookered. We would be in checkmate. Fortunately, 2021 has a little bit of snow. It's not ideal, but as I said in the previous ones, we can work with that. Okay, so there's a number of images or variables that we generate. So we go to our project script, and you see I've made the dates now from 2021 the 5th month to 2021 the 10th month, because it's a sum. So I'm really now, just adding all these things, so I can get some indication that there's snow. Okay, so I've expanded my time period within 2021 to cover more times, so that I can add up all the little bits of snow and hopefully get one picture that's a lot of snow. Okay, because the snow were quite sparse and scarce in 2021. At least there was, but it was sparse and scarce. Okay, anyway. So all the other ones I've also now made the dates. You can see they're all now 25th of the 5th month to the 10th month 2021. So that's our climate. So at least we'll have data for that. And then obviously I've moved my Sentinel images, the date for that as well, the same. So at least we'll have Sentinel. And then I'm bringing in my normalized difference snow index data product. I bring that in. Remember, that is this one that I'm bringing in. It's a 16-day product. Now, why 16 days? Because Sentinel is 60 days. That's okay. So Sentinel, every 16 days, there's an image of your region of interest, and that's why it's 16 days. If it was every 8 days, that would be an 8-day product. And if we go down, it says there that the normalized difference snow index is used to identify snow. Okay, based on the characteristics, high reflection of the visible portion of the spectrum compared to the mid-infrared. NSD is computing using green and mid-infrared bands, and has a range of 0.1 to 1, because it's an index. Okay, so there's you can go and read further on it, and there's our script to get started. So I just copied and pasted in our script as per normal. Obviously I clipped it For our region of interest, I've changed the dates and I have reduced it to a mean, because if it's every 16 days, you can count how many images there would be. 1, 2, 5, plus minus 5 times, it's plus minus 8 index images, and we reduce it by median. Okay, reason why, because we've showed it's a better option. There's our visualization parameters, and I add it to my layer or to my maps. There it sits. NDS, you can see normalized difference snow index. There it sits. Then I calculate using my Sentinel image. You see, there's my Sentinel image. If I go up with Sentinel image, this one here is the median image of this image collection, of Sentinel image collection. That period, snow, clipped, etc. Again, a median. Like for like, median. So I take Sentinel image, select band 4. What is band? Oh, it should be band 3. Should be band 3. Subtract band 11. Then band 3 and add band 11. Okay, band 3 minus band 11, band 3 plus band 11. Have a look there, band 3, subtract band 11, etc. Band 3. Okay, so let's run. Let's have a look what happens. There's nothing red, so all our stuff is good. Let's unselect all the climate and terrain images or maps or layers. We're not interested in that as well. And this is what we're going to get. Remember, save, always save. Okay, so let's give it time to load. And let's make sure all our dates are fine. It's clipped. We've got all our bands. So it's band 3. Band 3 is blue band, red, green. Sorry, green and blue. And, okay, so it seems like we're all good to go. Okay, so now let's identify a location that had snow, and that I'm using this. Okay, so there's a location there that had snow. So let's zoom into it. Let's go and see what the snow looks like. Great. That's good. Let's zoom in again. That's the beauty of Sentinel. We can zoom in because of the high resolution. There's some snow indicated. This is the snow product. Remember the Terra snow product? It's indicating or suggesting there's snow here. So now we're going to overlay that with the Sentinel image to visually confirm whether there was snow. Look there. It aligns pretty nice. So let's zoom in a little bit more. Before it gets too blurry, let's zoom in until a little bit so that we can make sure, because using the inspector is quite sensitive for the right locations. Okay, so that suggests there's definitely snow. Definitely snow. If we bring in the snow cover, you can see the white indicating this. And the reason why it indicates also this area here is simply because of the spatial resolution. Because remember, if you look at it now, let's look at it. You see, that's white goes all the way there. So that's why the spatial resolution matters. But anyway, now the point is, there's snow. We found snow. There's some snow there. There's some snow there. Okay, so let's overlay this with the normalized difference snow index data product. This one here, which have a range of -1 to 1. So this one here. Let's overlay that and see what comes in. And blues, you can see there's some that indicates. You can see the color, dark blue and blue. You can see there's no snow there. This seems to indicate snow. If we go to the color scheme, visualization parameters, let's have a look. This is the visualization parameters. I would assume that color. Let's quickly go and copy and say, okay, what is that color? That color is dark blue. Okay, so that's dark blue, and I would assume this color then would be that light gray bluish color. Let's have a look and see. Yeah, white, basically white. So this would be -1. this will be roughly about the 0, and this will be positive 1. So that sort of should be possible. We'll have a look anyway. Okay? Let's not speculate. We'll have a look. Let's overlay this with our normalized difference snow index, the one that we've calculated. The one that we've calculated. And that shows that. Now you can see the spatial difference in spatial resolution. Huh? Have a look there. You can clearly see the difference in spatial resolution. That's why I wanted to use the Sentinel images as well, and not just the normalized difference snow index as per the data product, because of the spatial resolution. So let's have a look. So again, these all seems to suggest, if I unselect them, you see, okay, let's do that. You can see it indicates the snow period. In fact, in my mind, this is much better than the data product. That's the data product, that's the one that we've calculated. As I said, in my mind, the one that we've calculated, the normalized difference snow index derived from Sentinel that we've calculated, seems much better than the data product. That's my opinion. And they all align quite nicely. Okay, so let's have a look at the inspector. I'm going to unselect because I want to be very specific with what I'm looking at. Let's look at this position. I want to make sure I'm in the thick snow. This is visually. Let's have a look and see. Yeah, thick snow. 665. High snow cover. You can see it's very high. Slope quite steep. Aspect is again southwesterly, and hillside. Lots of shading area. There's just a summary. There's our bands, our reflectance. You can see there's our spectral reflectance for the snow. Let's have a look at our indexes. Ooh, look at that. So our normalized difference gives us a value of 0.013. Okay, and then our calculated normalized difference now is a value of 0.62. Now let's go back to this tutorial. It says that values above 0.42 are normally snow, and this is definitely above 0.6. Above that, and this value is close to 0, which I would assume within this value is close to 0 would be snow. Value close to -1 or 1 or positive 1 would be no snow. So I assume, we'll have a look now, that we want this value to be as close as possible to 0. Then all the stars align. Let's have a look at another place. Let's look at this position there. Now let's look at something there. There's definitely no snow. Let's click there. And the reason why I would do this is to have a look at my values now. Specifically the data product, the normalized difference snow index data product. Have a look at that. That's going to be okay. So that's going quite a bit to the -1 side. Okay, let's have a look at that. So our assumption that the normalized difference snow index data product values would be close to, and it's exactly okay. So let's look at now another snow area. There's a little bit of snow there. Let's drill in. I wanna capture this area, that white area here. That's what I want to capture now. Okay, so let's wait quickly for these things to disappear. It's loading, it's loading. Let's have a look at this. Okay, okay, so where was it now? Was it this one here, or was it this one here? Okay, let's use this one here. Okay, that one. Let's try this one. Okay, so let's have a look and see what the snow is. 127, so that's not a lot of snow. It's quite steep. Let's have a look and see what there's our reflectance. Yeah, not too much of snow there. So that's most probably not. Okay, so let's have a look at this one here. Let's look at that one there. Click on that. That's why you have to zoom in quite a bit, and that's why spatial resolution matter, because we need to be quite accurate when we use our inspector. Quite a lot of snow. Okay, so quite a lot of snow. Let's have a look and see what our spectral spectral. Let's have a look. Yeah, you can see 0.73 and 0.15. So that's clearly the closer to 0 you are on the normalized difference snow index, the data product. We want the value as close as 0 because that indicates snow. And then with the one that we've calculated from Sentinel, the normalized difference snow index derived from directly from Sentinel, we want the value to be as high, to close as possible to 1, preferably from about 0.42 or 0.5 onwards. So we sort of understand those parameters. Let's have a look at this one here. Let's have a look there. Okay, let's see what that value looks like. A lot of snow again. Not going to go for all these others. What's the temperature there? Minimum is 2.6. So that's not a lot. That's very close to, okay, 0 and that. So yeah, so that seems to confirm our suspicions or our numbers and stuff. So, and if we just activate it, let's have a look there and see what those images look like. And interestingly, when we look at this, you can see the bluish color versus the white color of the snow. Normally the blue color is much more deep snow than the white color. The white snow is normally more flaky and more loose, where the green snow is much more thick, much more compact. I talk under correction, but that's my understanding. One will just have to go and check it out. So what we're interested in is that green color snow is almost like a watercolor, deep blue, and that seems to be the dark snow. If I can vaguely remember my geography and National Geographic of glaciers, it's the white on top is not the cold one, it's that blue part which is a cold one, and you can see that. And I as I said, I like this derived normalized difference snow index, the one that we derived from Sentinel. First of all, it's got the spatial resolution is quite nice, and second of all, it is much more visually appealing than if we use the data plot. But again, we can play around with these visualization parameters to make it better. You don't have to take this, but okay, that's again where the inspector comes available, important, relevant, is to determine the underlying statistics. But you know, it's important that you use your inspector at the right location. Okay, so that's quite a nice one. Again, as always, we've used the normalized difference snow index data product from Google Earth Engine, and when we also generated our own normalized difference snow index from our Sentinel image by using band 3 minus band 11 divided by band 3 plus band 11 band 3. Let's quickly just have a look and see if we go to Sentinel data products. What is our Sentinel? We go to our Sentinel, we go to, remember we're using Sentinel 2, and we're using surface reflectors. You'll see it's only available from 2017. And that's why that big snow periods of 12 and 14, unfortunately, yeah, that's missing. Okay, so let's have a look at the band. What is band 3? Band 3 is green, and therefore the green snow. No, who would have thought, huh? Who would have thought? So that's why it's emitting quite a bit of green. That's why we're looking at the green, because the more green it emits, you know, that's the green color. Okay, so that's fascinating. And then band 11 is the short wave infrared. Okay, so those are the two bands that we combine, green and short wave infrared. Okay, so that's the two bands that we operate in. Okay, so that's just confirming this one. So this one, in fact, is one on the visual infrastructure. Okay, so that's what they mean is what visually what we visually see, which is the red, blue, and green. So remember, in our modus, where is it now? Did I delete it now? Why? Oh no, here it is. This is our visual bands: blue, green, and red. Okay, so band 2 blue, band 3 is green, and band 4 is red. Okay, and there's our formula. So that's quite neat, but as I said, yeah, I prefer this particular one. I really prefer the one that we've calculated. I think that's a better option to do. And obviously we can now, if we do that, and let's take this out, let's take this one, and shall we, yeah, so let's quickly do this, and we apply, we increase its transparency. Let's see what happens now. Or should it be the other way around? Okay, it's still taking a bit of time. Still loading. Maybe we should take that. Well, you can play around with the color scheme. You can play around with the transparency, etc., etc. As I said, we want the value to be as high, so let's make that one. Let's quickly make that red. Press OK. See what if we press apply. Let's quickly make that full. It's not going to give us red, it's going to give us, oops, I'm working with the wrong one. I want to work with this one, man, not that one. I want to work with this one. Make it more transparent, make it 50, press apply. You see it fits the snow almost to the T. Yeah? You can see that, almost perfect. Let's make it red, see what that looks like. Apply. Okay, so that's still, let's make it red. Okay, make it also, make it yellow. I'll make it that color. Apply. There we go. Now that looks better. You can see, you can clearly see where the high snow is. You can see the blue. This is the red, is where the blue snow is. You can see that, that's the blue. So I go there, you can see the blue. The blue of the green snow, the heavy snow. And so if we click there, let's have a look. If we click there, it's going to be, okay. It should be quite a lot of snow. Yep, quite a lot of snow and cold, yes. Close to 0, almost 0, close to 1. Oh, what a beauty. But when a plan comes together, there's another one of those. Where's deep blue? Let's have a look and see. Yeah, you can see the deep blue colors. So fascinating, interesting stuff. I like it. That's wonderful stuff. Yeah, no, why not? Why not? And obviously, underlying it is our snow cover. So we can actually save this as our snow cover image. Yeah, why not? And because it's got a perfect spatial resolution. The only thing is, we'll only be able to do that from 2017 onwards because of the Sentinel images only being available from 2017, which is a pity. We can't go back to 14 and 15. Anyway, I rest my case to honor, as they say. Okay, thanks guys. Thanks for joining me. That was interesting. I learned quite a bit. I'm thoroughly enjoying this journey. And again, thank you for accompanying me. Thank you for joining me on this journey. I don't feel alone. I feel welcomed, and I feel like like one happy family, remote sensing happy family. Please guys and girls, please like and subscribe and share the video. It makes a world of difference. I like it when I see the numbers increasing. It gives you Vuma to go forward. So please guys, remember, press those buttons. Sharing is caring, and then I'll see you on the other side.